Welcome to the laboratory X-ray powder data, fluoroapatite. In this tutorial, you will refine the structure of fluoroapatite using constant wavelength laboratory X-ray powder diffraction data. At the completion of the refinement, you will then prepare a drawing of a fluoroapatite structure. The structure is hexagonal with 4 different kinds of atoms spread over 7 different sites. The data was taken on a conventional Bragg-Brentano powder diffractometer. If you have not done so already, start GSAS2. Use the Import Powder Data from GSAS Powder Data File menu item to read the data file into GSAS2. This data option is set to read any of the powder data formats defined for GSAS2. Change the file directory to labdata/data to find the file. You will need to change the file type to any file. Select the desired file in the first dialog and press Open. There will be another dialog box asking, "Is this the file you want?" Press Yes to proceed. Select the instrument parameter file in the second dialog and press Open. At this point, the GSAS2 data tree window has several entries and the plot window will show the powder pattern. For this first step, we will take advantage of having an old GSAS2 experiment file with all the parameters for fluoroapatite. To import the fluoroapatite phase information from the desired file, use the Import Phase menu to see a pull-down menu. Select from gsas.exp file. The file selection dialog will still be set to the directory the data was found. Click on the desired file and Open to open it. You will see an "Is this the file you want?" dialog. Press Yes to proceed. A small dialog box with a phase name will then appear. We use the name Fluoro. Next, an Add Histograms dialog will appear. Select the PWDR item and press OK. The GSAS2 data tree should now have a phase entry of fluoro. The phase information will be shown here. You can see that the number of each kind of atom gives 2 formula units per cell. The Data tab will show the sample broadening information associated with the powder data set we just loaded. We will return to this window later when we consider the effect of crystallite size and mass strain broadening. You may have noticed that the background in this powder pattern rises significantly at low angles. There is also a less apparent rise at the high angle end as well. The default background function doesn't handle this very well, so we find the background item under the PWDR bank in the GSAS2 data tree and press it. The background window will appear. Change the background function to log interpolate and the number of coefficients to 9. This will put background points at the 2 limits and at equal spaces in log2 theta in between, so there are more where the background is changing most rapidly. A linear interpolation is then used to compute the background for all points in the pattern during the Rydfield refinement. Under the sample parameters, refine the histogram scale. You are now ready for the first Rydfield refinement. The histogram scale and background will be refined here. Press Calculate, Refine in the GSAS2 data tree menu. The refinement proceeds, and when complete, it will have an RWP of about 45%, and a small dialog box will appear asking to load the new result. Press OK. The windows will be updated and a new plot is displayed. Expanding the plot shows that much of the difference is that the calculated peaks are out of place. This is due to the lattice parameters. Also, that in this Bragg-Brentano experiment, the sample position is offset from the focusing circle. This is most likely the reason for Peaks displacement errors in laboratory data, not the 0 point. Go to the General tab for the phase fluoro and select the lattice parameter flag called Refine Unit Cell. Then go to the sample parameters under the powder bank in the data tree and select the sample displacement flag, and make sure that the diffractometer type is Bragg-Brentano. Now do the Rydfield refinement by Calculate, Refine menu on the GSAS2 data tree window. The plot will look something like so. It has noticeably improved with an RW around 14.4%. Close inspection shows that most of the differences are in the widths of the peaks, so we should refine crystallite size and mustering parameters next. Select the phases fluoro item in the GSAS2 data tree, and then select the data tab and set the refined flags for both size and mustering. Next, do the refinement. Press the Calculate Refine menu item. Do not be alarmed about how the RWP jumps around on the progress bar. That is a consequence of how the algorithm does a least squares minimization. The result in the end is much better, with an RWP of about 11%. Next, we can refine atom parameters. Select Phases, Fluoro, and then go to the Atoms tab. The phase data for fluoro window will display. Double-click the refined column header. A new window will show the refinement controls. Select the X coordinates and U thermal parameters and then press OK. The Atoms tab will now show the new refined flags. Now run the refinement. Press Calculate Refine menu item on the GSAS2 data tree window. The result is much better with an RWP of about 9.5%, and the plot is pretty much the same as before. And the atom parameters are now shown on this table. The refinement is now essentially complete. What we like to now try to show is the contents with the phosphate ions as tetrahedra and the calcium and fluorine atoms as balls. By finding the phases/flora in the GSAS2 data tree and selecting the Draw Options tab, we can now see the phase data for fluoro window shows the drawing options. The plot will show a new tab marked Fluoro showing some balls in various colors. A unit cell box is drawn with 3 colored edges, red, green, and blue for A, B, and C axes respectively. A multicolored 3D cross is at the center of the plot. Notice the sliders in drawing controls. You can change them to change how the structure is displayed. Press the Draw Atoms tab. This will show the list of atoms that are drawn in the picture. This is a copy of what is in the atoms table. There are columns that allow you to change how the atoms are displayed. Their labels and their color are all controlled on an atom-to-atom basis. Now, if the contents of the atoms table change, by refinement for example, then you must manually update the Draw Atoms table by erasing all the draw atoms. They are then automatically refreshed from the atoms table with the new values. You would do this by selecting all the draw atoms. Double-click on the blank in the upper left corner of the table. All atoms will be highlighted in dark gray. They will be all green on the plot. Then press Edit, Delete Atoms in the Draw Atoms menu. All the atoms will vanish and then reappear with updated values. Now we can draw the structure assured that we are using the final result from the refinement. To build the structure model, we want to show with phosphate tetrahedra and balls for the fluorine and calcium items in a unit cell box to do the following steps. First, we're going to select all the atoms in the Draw Atoms tab by double-clicking in the upper left corner box of the table. All atoms in the table are then displayed in dark gray, and they will be highlighted in green on the drawing, indicating their selection. Select Edit Figure, Fill Unit Cell from the menu. The drawing will show the unit cell filled with atoms in positions equivalent to the original set, and the Draw Atoms table will then have all of them listed. The symmetry operator column in the table shows the symmetry operator number and a unit cell translation used to generate that position. Double-click on the column labeled Type. A small dialog window will appear with a list of elements in this structure. Select P by checking the box and then pressing OK. All the phosphorus atoms will be bright green and they will be highlighted in dark gray in the table. Select Edit Figure, Fill CN Sphere in the menu. Each phosphorus atom will now have its full complement of 4 oxygen atoms. Repeat the selection of the phosphorus atoms once again. Select Edit Figure, Atom Style from the Draw Atoms menu. A small dialog box will appear with a list of possible atom drawing styles. Notice the first one is blank. that will cause the atom not to be drawn. Select polyhedra and press OK. Each phosphorus atom will be drawn as a brass-colored polyhedron with too many faces to be a tetrahedron because a nearby Ca atom was included. However, this will be fixed in a moment. Now double-click on the type of column label yet again, but this time select the oxygen atoms. Select Edit Figure, Atom Style, and pick the blank entry and press OK. The oxygen atoms will vanish, leaving some odd polyhedra and the calcium and fluoride atoms. Select the Drawing Options tab and change the bond search factor to 0.80 and press Enter. The odd polyhedra will immediately change to tetrahedra. You can adjust the van der Waals scale to make all the balls any size you desire. If you don't like the fact that both calcium and fluoride are in a very similar green, you can change this. Select the Draw Atoms tab and then select all the calcium atoms. In the Draw Atoms menu, select Edit, Atom Color. A color selection dialog box will appear. The steps for changing color is to either A, choose your color by finding it in Basic Colors and pressing OK, or B, press Define Custom Colors and move the cross around on the spectrum display, and also set the vertical slider for the luminosity and then press OK. The drawing will now show that color for the atoms, and the color will appear in the Draw Atoms table. If you don't like your colors, select Edit, Reset Atom Colors to put them back to their default colors. Next, we'll see how GSUS2 can compute all the distances and angles among all the atoms you select in the atoms table. It can do this with controls on the range of atom-to-atom distances to consider either globally or by atom type. To start, select the Atoms tab in Phases/Fluoro. Select the first calcium atoms by clicking on its row label. Add to the selection the other calcium atom and the phosphorus atom in the same way with the Control key down. All will be highlighted in blue. Select Compute, Show Distances and Angles from the Atoms menu, and a small dialog box will appear. Here you have individual controls on various atom radii to consider for both distance and angle calculations, as well as global search factors. Considering our experiences with drawing the phosphate tetrahedra, the bond and angle search factors may be too large for this case. Change both to 0.8 and then press OK. GSUS2 will then display on the console formatted tables of individual atom distances and angles with ESDs as appropriate for the two calcium and phosphate atoms. There's probably too many bonds shown for the calcium 1 atom and no angles given. You can repeat the calculation with somewhat smaller calcium radii to fix this. Setting the bond and angle calcium radii to 2.1 and 1.9 respectively, and the angle search factor to 0.95 gave this result, which is probably much more reasonable. This concludes this tutorial for Rite field refinement of fluoroapatite. Thank you for listening and good luck.